Okay, let's begin with question number 10. Okay, let's move it to a whiteboard, please, and start on that. So the function f is defined by this thing, this fx equals to ln x whole thing square. Please take note, not ln of x square, for x positive, so that the ln is defined. And being real, I mean. Okay, so the diagram shows a sketch of the graph of the y equals fx, and the minimum point of the graph is A. So the point B is x coordinate E. So it's the two things. So state the x coordinate of A. So how do we find the x coordinate of A? So the x coordinate of A happens when the minimum is occurring. So actually, by the picture, they want you to do by the picture, actually not by using the idea of minimum. Just mentioning the minimum is an extra. That means we must solve for fx equals to or y equals to 0. So you can easily see that this is same as telling ln x square is 0, or in other words, a ln x is 0. Okay, so x will equals to, because ln is base e, so e to the power of 0. That means basically like log base e x, this and then just anti-log it. So x equals to 1. So basically the x coordinate here is just 1. Okay, it's done now. Okay, so show that that means the double differentiation, second differentiation, sorry, of x is 0 at b. Because what we do is, let's say we talk about fx equals to ln x whole thing square. Okay, we're doing a bit of like a chain rule thing. Okay, so when you do the first differential, what you do is imagine just like the 2 times in front. Think of it like you're differentiating x squared. So ln x, that means a -1 right, the power like that. And then chain rule, you multiply, differentiate inside. So in differentiate inside, it becomes 1 over x. Ln x differentiated is 1 over x. Okay, so that means, so 2 ln x and then whole thing over x. Okay, now to do the, what we say, the next part, it's kind of interesting because we let u equals to ln x and v equals to x. That means, so from here, I can easily say that du dx, so good to write it using the quotient rule. Du dx is 1 over x. Here, comma, dv dx is 1. That means that, so I'm going to do f double prime, the second differential, as this function is like something like 2u over v, by the way, in terms of the functions u and v. We use the quotient rule because there's divide there. Okay, that's the reason why. So the constant 2 just maintain such, just maintain only, sorry. Speaking Malay. Okay, so then we do v du dx, minus u dv dx, whole thing over v square. The v square part, I'm just going to write outside here like this. The reason being, see, we just want to show that it's going to be 0. So the v square part is not really necessary for the second part. I mean, they're showing 0. So the focus is on the v, so it becomes an x. So du dx is 1 over x minus u just copy only, ln x, dv dx is 1. So we want to show that this becomes 0. Okay, so to show that this becomes 0 at b, okay, let's just put this as 0 and then we try to solve it. So it's obvious that denominator cannot be 0 and it doesn't affect that. 2v squared is just a positive constant. So the brown values is what we need to make it is 0. So 1 minus, this is ln x, which is 0. So ln x equals to 1. So it goes back to x equals to e to the power of 1 anti-log, which is x equals to e. That is at b. At b unit, x equals to e. So that's how we do that. Done. Okay, let's do the third part. This is the hardest part of this question, which is using the substitution. So they also teach which substitution to use, which is the x equals to e to the power of u. So I'm just writing it so more space. Just take note. So what you do is whenever they talk about substitution, we differentiate it. So dx, du, because differentiate e, you get back e. So it best becomes e to the power of u. That means, in other words, what I'm trying to say is the dx can be replaced with e to the power of u du. This is the technique for this. Okay, let's think about it. So that means the integration. So the area bounded by the x-axis, blah, 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 and the line x equal to e is definitely this area and the part of the curve. They're talking about finding this area. Please remember that this is 1 So I'm just going to write it in terms of the normal way first. It means the green area, okay, is equals to integration. Actually, the bounds are 1 to e, right? 1 to e of that given curve, which is ln x whole thing square in dx terms. So with substitutions, yeah, please take note. Substitution must be careful of the values. The boundary values need to change. That means the integral limits. Sorry, the integral limits. So the integral limits, if you want to change to u, please take note x equals to 1. Aha. So using this equation, the same equation here. Sorry, a spacing thing. Yeah? So we put it as e to the power of u. Similarly, the other boundary is x equal to 0. Where am I picking x equal to e? Where am I picking these two boundaries up? Based on my limits here, integral from 1 to e, as you can see, this and this. Please take note. So this will become e to the power of u. So solving for the value of u, we see that u is 0. This one is u is 1. That is why the new integral limits will be 0 and 1. Aha, for in terms of u. That's why we change it to 0 to 1. And then the ln x, see the interesting thing about this substitution, something I didn't write yet, which is it implies that ln x equals to u, right? Do you realize? Aha. So that means this becomes u square, and the dx part, please take note the dx part here, which is from here, just to change the color to show. Aha, this one dx becomes e to the power of u du. Oh, e to the power of u and du like that. So now it's purely entirely in u. So basically, you can see that is exactly this statement. Show that the area is bounded by this. So done. This is part 3. This is how we show that it's equivalent to integrating this part. Okay, there's one more thing. Maybe I didn't bring up the question earlier due to no space. We just get that part, please. Hence or otherwise, they say, find the exact value of this area. That's missing that. That's how I missed when I cut and paste. I put it nicely down here. Okay, so that we can see it. Ta-da! We put up here. Maybe easier to see like that. Okay, there we are. So how do we find the area? So this is integration by parts, the substitution, and I think makes it doable. I mean, this part. So we just focus on just now for the fourth part. Even if you didn't get the third part, you couldn't prove it. Please just attempt it. That means just go ahead and integrate this part. Maybe you can get the 3 marks from here. We never know. So to do integration by parts, I'm just going to show a formula that I'm going to pull off from the internet as well. From Math is Fun. Okay. I just need the formula. Okay, this one. So here we are. The general formula looks integration by parts like this. One of the formulas or ways, one of the ways of writing it. There are a few ways of writing this formula. Please take note. Okay, and it's the same thing. It's just the way we view it. Okay, so from here to here, please don't get confused. So integrating from u to 1, 0 to 1. Let's go ahead, please. So we must choose our u carefully. On this one, you can see that the one that cannot integrate, we try to write it outside. That means easier, and the one that can differentiate easily. In this case, it doesn't really make much of a difference. So it's going to be this one. I'm going to put it like that. So that means, so it's going to be u squared like that. Oh, sorry, what am I writing? Okay, u squared first. Sorry. I'm writing here and pointing there. I got confused. Okay, this is a u square. Let's follow this version. So u square first, we write, and then integration of the v. That means it's kind of like that. E to the power of u there against du. Okay, adapting the formula. So minus integration of differentiate that place. So differentiate of u square is 2u. And then in the bracket, you have the integration of, the v itself. That means e to the power of u du. And then du. In this terms is all du. And this is how the formula looks when adapted to this situation. Integration of u is just remains, e to the power of u just remains as e to the power of u. That is the advantage of this. So we can just do it easily. Here we just take out a 2. And then we look at this part. You realize something fascinating, which is here becomes a u. The e to the power of u just become e to the power of u again. Integrate that, so no difference. E is a function. When you integrate, you get the same thing again. And then we need to do a second. This is the hard part or the trick. So we have a u square here, e to the power of u minus 2. And then this part now we need to change it a little bit, please. We need to do an integration by parts again. Oh, so did you notice the u square became 2u? Now the u is going to vanish because when you integrate, differentiate it. So that is how we choose this component is important part. Just giving a tip how to do that. It's okay. So u and then integration. Aha. Oh, yeah, what am I writing? u and integration of e to the power of u du. So using the formula for the second time, differentiate u now becomes 1. Just to emphasize that, I'm just showing that is integration symbol that. And then in the bracket, integration of u to the power of u du. Aha, so like that. And then there's a du outside for this. And then only the bracket. Okay, so meaning that, so let's try to simplify this and we should get the answer. So e square e to the power of u minus 2. Oh, this becomes like what? Dun, dun, dun. Okay, this is u. This whole thing's become e to the power of u minus e to the power of u. Sorry, forgot something. There's an integration on that. That means one last integration on that, du like that. Like that, did you notice? Then just becomes, okay, u square e to the power of u minus 2, let's do it slowly, just to avoid errors, e to the power of u, this one is integrate again, also becomes this thing, sorry, e to the power of u, right? But this whole thing, if you notice, I skipped something, which is just is definite integral. So I'm not adding a constant, but the writing is a bit complicated. So what I wanted to do was just put a giant box like that. And then you can put the 1 and 0. If it's kind of like too lazy to write, I just put like that. So I should write the 0 and 1 here. So I should put 0 and 1 here. You know, I'm trying to say, you can write it later. So like that. Okay. So all these are separated 1, 0 like that. So just need to be evaluated now at 1 and 0. Aha. And this one integration, blah, blah, blah. Okay, then there's some kind of like this one we must put here actually inside. But it doesn't matter. You can even like kind of like collectively put it here now. Aha. So the 1 and 0 thingy. Okay, we need to evaluate it at 0 and 1, and then we'll get the answer. Okay, let's just evaluate that manually. Let's just show that emphasis. Okay, so 1 square minus e to the power of 1 minus the 0 means the whole thing can vanish. So minus 0. Then we have this minus 2 here. So in the bracket, as you all can see, we put the 1 means it becomes 1 and e to the power of 1 minus e to the power of 1. Aha. And then I need to subtract with the 0 there. So 0 means the 0, 1 is this thing like a bracket there, 0 dot e to the power of 0 minus e to the power of 0 like that. And then we put the bracket, close the bracket, please. And then let's try to simplify it. This becomes e to the power of 1. And then this becomes minus 2. And then in the bracket, let's simplify all of this, please. So e minus e. And then this is plus 1, isn't it? The bracket. Am I doing it correct? Just checking, sorry. The minus, yeah. Okay, it's at the time 0. So minus plus, right? Plus e to the power of 0. Yep. So it just becomes, the whole thing is just e here. This bracket 0 is like minus 2 and 0 plus 1. And the final answer is, it's correct, it is e minus 2. We just leave it as e minus 2 as a constant. It's okay. We want to evaluate it. This thing, so, because you see the word exact, sorry. The word exact means you must leave it as e, yeah? Exact, the constant e. Thank you.